Okay, let's do a sample problem. It says the particle collision frequency is 2.5 times 10 to the ninth per second for oxygen gas at 250 Kelvin. What is the pressure? Well, Z11 represents the particle collision frequency, and we know that it equals pressure, Avogadro's number, RT, cross-section, square root of 2 RT over pi molar mass to the 1/2 power. By the way, this right here is the average speed formula. First, we need to find the cross-section of O2 gas. Now, one nice little shortcut is to look again at table 16.1 inside your textbook, and you'll see that the cross-section is equal to 0.4 square nanometers for O2. But we can't use square nanometers. We have to convert to square meters. So we multiply times 1 over 10 to the 18th square nanometers for every square meter, and that's going to give us a cross-section of 4 times 10 to the negative 19 square meters. Okay? And next we'll also need our molar mass for O2, which from the previous problem we saw equaled 0.032 kilograms per mole. Now at this point we just need to plug all these numbers where they're supposed to go into this equation for the particle collision frequency. And so we'll put in 2.5 times 10 to the ninth inverse seconds equals P, and then Avogadro's number 6.022 times 10 to the 23rd, 8.314 joules per mole Kelvin, and 250 Kelvin for the temperature. Particle cross section, 4 times 10 to the negative 19, square root of 2. And then here, 8.314 joules mole Kelvin times 250 Kelvin divided by 3.1415, that's pi, times 0.032 kilograms per mole. And then this is to the 1/2 power. When we multiply this all out, this becomes 6.67 times 10 to the 4 times the pressure. So then when we solve for this algebraically, we're going to get a pressure of 3.75 times 10 to the 4th pascals, which is about 1/3 of an atmosphere. Now let's say there's another part of the problem that wants the mean free path. What is the mean free path? You could look up the formula that I gave you for that, or you could take the shortcut. The mean free path equals the average speed divided by Z11. And if you looked ahead in your problem, you could have plugged that part into your calculator independently and gotten the average speed. But what goes in here is 406.7 meters per second. That's what I calculated as the average speed right there. And then we're dividing by what the problem gives us for the collisional frequency. And in the end, we get 0.63 times 10 to the negative 7 meters. And that is how far the particles travel before running into each other for oxygen gas at about 1/3 of an atmosphere. This is a very short distance. That is approximately the width of a medium-sized virus. That's how far oxygen particles in this situation are traveling before they run into another oxygen particle on average.